And let's start with just a review problem from what was covered last time around. So there's light and it's going to be shining just directly on this mirror. And bouncing out the same way it came in. So the bounce is going to increase the amount of pressure. So at sea level, air pressure is about 100,000 newtons per square meter. So how intense of light would you need to get as much pressure as you would from air pressure? See if you can work through. It's a lot. It's yeah, almost that simple. The thing that throws it off is the mirror. Yeah, so the average value of our uh, energy transmission is the same as intensity. So yeah, it's so if it was hitting an absorber, it would just be intensity divided by the speed of light. But because it's a reflector, uh, it's twice the change in momentum, so twice the pressure for a given intensity of light. So because of that, we just need half as much as what you calculated due to the reflecting nature. So So we've got newtons per meter per second, or Newton meters per meter squared per second, or joules per meter squared per second, or watts per meter squared. So the units do work out to around 1.51 times 10 to the 13th watts per meter squared. Right. Yes, and the bar over something means average value if there's no arrow on the bar. Uh, so just want to give just a little picture of all the kinds of light there are. Uh, so if we look at the wavelength, meters, and the frequency in hertz, we just have light traveling through a vacuum, then the greater the wavelength, the lower the frequency. So if we have something which is 3 meters, that would have to get 10 to the 8th hertz. Because the frequency times the wavelength will give us the speed. And if we kind of make a logarithmic scale of all the kinds of light that we can make, so the shorter wavelengths are going to correspond to greater frequencies. And this keeps going. So over lots and lots of powers of 10, the kinds of light that there are, there's a lot of variety in what qualifies as an EM wave, and still relevant and produced and observable. So the part that we can see of this spectrum of waves is not so big. You can see just kind of a little window in here. $750 nanometers or so. Up to around 400 nanometers. So a pretty narrow band. I probably drew that too big for the scale that I'm on. And inside there, you're going to get red, and blue, it's violet on the very end. And the full rainbow in there. And past that, so moving to shorter wavelengths, which for a given photon, if you're going to look at it from a particle's perspective of light, has more energy and higher frequencies. So we get UV light and X-rays. And gamma rays. The boundaries between what's an X-ray, what's a gamma ray, aren't the best defined. Like there's a certain one cutoff frequency. If something's made from a nuclear process, it might be called a gamma ray. But if it's made from an electron moving down to a lower energy state, it might be called an X-ray, even if they're just about the same frequency. But those are the very, very high frequency kinds of light with very, very small wavelengths. On the other side of what we can see, there's infrared, then microwaves. So something a microwave oven would use or radar would use, and then radio waves. So the difference between a radio wave and a gamma ray is significant, but it's not that they're like an entirely different kind of thing. It's just change the wavelength of it by a whole lot, and it's now a gamma ray instead of a radio wave. Right. I think we have about enough electronics knowledge to look at just the basics of how a radio can work. There are definitely more. Wait, does someone have something?
No, I think I just hit my space bar.
Oh, no worries. More complicated styles of radio than the simplest radios you could make. But if you've got, electromagnetic waves coming in and you hit an antenna, and you ground your antenna. So if there are electric fields that are hitting this, it's going to try to make an electric field inside of this conductor, which is not an easy thing to do. So charges move in response to that. So you can have charges moving within this antenna. And you can either hook this up directly or maybe use some mutual inductance. To get current flowing in a different circuit. But important part, the wave hitting this conductor is going to cause charges to move within it. And the current of those moving charges are what will be giving us the energy and, more importantly, the information. So if you had a different amplitude of wave hitting this, you would get more charges moving. So this can connect to a capacitor. So this, we've got an inductor, we've got a capacitor. So this bit here is going to have a resonant frequency, which is important for picking out the radio station you want to hear. So you could either use a variable inductor or a variable capacitor to be able to tune what radio station or what frequency of radio waves are going to effectively drive current in this little circuit here. And then you pick that up. Probably take it through an amplifier of some kind, which I don't think we're really going to have time to get into amplifiers. Pretty cool. But the important ideas for our perspectives are the wave drives some current and the circuit can pick out the relevant frequencies. So radio waves are higher frequencies than what you would hear. So you don't actually listen to the signal of the radio wave. If it's an AM wave, there would be, say the sound wave you're trying to actually hear. This would be your signal that you want to convey using this radio wave. It could be an audio information or just anything really. And you could have just a perfectly regular higher frequency signal. And what it does is this is the carrier. This is sort of like your desired signal. So if it's an AM radio, that means amplitude modulation. So it takes this carrier signal, and when you want to send a peak, you just send high amplitudes of the carrier signal. And when you want to send a trough, you send low amplitudes of the carrier signal. So it modulates or varies the size of the wave that's coming. So keep the original frequency, but it just gets big or small. So you'd actually transmit this way. This is our total signal. So as it got larger in magnitude, you'd get bigger currents flowing in this resonant area over here, which is going to send, if you just trim and only take the peaks of the wave with your transistor amplifier, you can just get that and hear the signal you want to hear. FM signals are a little bit more complicated. Instead of varying the amplitude or the size of the wave to match your desired signal, they vary the frequency of the wave. So it could just go high frequency for a peak, low frequency for a trough, high frequency, and low frequency. It's a bit more complicated, but I think it different way of sending information.
Are there like strengths and weaknesses for like using different types of waves then?
So as it's used, FM stations operate at higher frequencies. So you can there's usually the ability to, yes, carry more information in FM. So a higher frequency has more repetition per second, and you can get more information out per second in an FM wave. It also tends to be more noise resistant. So if you added on top of an AM signal just a little extra noise, it can interfere with it, I believe, a little more strongly than you would be able to interfere with an FM. Should be able to be more just random noise would probably interfere with your signal less if you're on FM and AM, so you should get better clarity. For making it, it's easier to make an AM radio. It was the first one. Right. That's just a cool thing. Right. Let's move on to something new. So light. So far focusing on the wave model. And the wave model is really good for picking out fields. So it deals with polarization well. It deals with, by polarization, I mean you could have two waves traveling the same direction, but one has the electric field pointing up and one has the electric field pointing sideways, and those are different waves. So the wave model is good for that. For interacting with things like antenna, big scale things, does well. There's a particle model of light where you look at light as photons, which is good for quantum mechanical behavior, looking at how light would interact with an atom. And we've got the ray model of light. So it's often said that light travels like a wave, interacts like a particle. But for the ray model, it's not a wave, it's not a particle, it's just a line going in one direction. So the perks of this model aren't that it can explain things better than the other models. Its biggest perk is that it's easier to use. So light It's something like that. Just travels in one direction. This is not exactly true. There are ways of bending light. Light can do things that cannot be explained in a ray model picture. But a lot of the things we do with light can be explained using a ray model of light. So even if it's not the most close to the fundamental physics, it is a very practical model of looking at light, especially for things like optics. So for our ray model, light travels at the speed of light, going straight until something interferes with it. So it could get absorbed or it could be reflected. But no, that's just gonna go, which is pretty easy. Lines aren't hard to deal with. But it can be kind of a shift from our previously more advanced picture of a wave in electricity and magnetism to just simplifying that down to thing traveling in one direction. So when it hits something, it could be absorbed, at which point the energy from the light just will go into the thing that it hits, and that's the end of the light. It's been absorbed. It also can reflect. It could transmit to where it just passes through it, but let's look at reflection. So two big kinds of reflection are the mirror-like reflection or specular, where if it hits it, it's going to bounce like you would think it should from a mirror. So if it comes in parallel, it's going to bounce out parallel. And if this is normal to the surface, our rule for specular reflection is that our angle in or our angle of incidence is equal to our angle out or angle of reflection. So you might not have heard it in these terms before, but if you had to make a picture of what light does to a mirror, it's what it does. It just bounces off of it. If you go straight into a mirror, you go right back the way you came. If you come in at a glancing angle, you leave at a glancing angle. So this is specular reflection. And our alternative is diffuse reflection. So if instead of hitting a mirror, you hit a piece of Teflon or a white piece of fabric, light's still going to bounce off of it, but it's not shiny. So if you've got diffuse reflection, one way of thinking of it is bouncing off of a rough surface. So if it comes into a rough surface, let's just say the exact angle that it's going to bounce off. So for a diffuse reflection, just bounces off all over. So instead of being orderly like it used to be, it has been diffused or spread out. So we're going to be focusing on specular reflections, or just like a regular mirror. That's not the only kind, but there's a real nice mathematical rule for them. So going back to specular, just for a simpler picture, if we've got mirror, ray of light coming in, ray of light exiting, our standard way of measuring the angles of these lights is not that angle. Just for optics, as a rule, our angles are measured from normal. So this is our angle of incidence. This is our angle of reflection. And the mathematical rule is really simple. Angle in equals angle out.
So the red line is perpendicular to the mirror, not the bisector of the angles?
It's both. It's definitionally perpendicular to the mirror. And our rule of reflection is the angles on either side of it will be the same.
So I guess naturally this begs the question, if you had a curved mirror, would you take a tangent at that point and use the vector normal to that tangent?
Yes. Yes, you would. We will be getting into curved mirrors. But yeah, for a picture of that, your prediction is dead on. If you've got curved mirror, and if some light comes in, hits it there, to figure out how it's going to leave, you take something which is normal to that part of the surface. You can't be normal to all of it. And angle in equals angle out. Theta incidence equals theta reflected.
It's pretty straightforward. I like that.
Yeah, nothing fancy with this law. Mirrors have a real good starting point. When we get to curved mirrors, a lot more math can be thrown out at them. How the curve affects things, where the images form. But just for a starting point, it's all good. Angle in, angle out. So let's try and take that easy thing and make it a little harder. So all of this is just going to be in the XY plane. So you can have mirrors which do things in 3 dimensions, but they're just hard to draw. So sticking with our XY plane. So we've got a horizontal mirror, a vertical mirror. I mean, this one is vert. And it has a horizontal normal vector, and our horizontal mirror has a downwards normal vector. So our light ray coming in is going to be 15 degrees above our x-axis. So what will its final direction be? So to work through it, you can start by just draw a simple picture and you'll probably get the right answer. But then try being a little algebraic in your approach to it to see if you can get there also. So we're going to get 2 bounces. Bounce off one then the other. So for just the picture, got our normal. We've got our normal. It's going to leave with this angle being equal to this angle, and then that incident angle being equal to that reflected angle. So this system does flip it around by 180 degrees. So a different way of looking at what this does is what the mirror does is it's going to flip the Y component of this incoming ray and keep the X and Z component unchanged. So just this plus Y part turns into a minus Y part. But the X component doesn't change, and if there was a Z component, it wouldn't change either. When it hits this mirror, it's going to keep whatever its Y component is. And if it had a Z component, it would keep that too. But bouncing off of this is going to flip all of the X components to minus X components. So if you flip both our X and our Y, that adds up to flipping around the whole thing for 180 degrees. To use this equation here, our angle needs to be 75 degrees. So then our angle here needs to be 75 degrees. and we've got 75 degrees here. We need to have 15 degrees here. And angle in, angle out, 15 degrees here. So we end up 15 degrees below the minus x-axis, if you want to describe it that way, or at 195 degrees, or however you want to describe that angle. So a cool thing that you can make with 3 mirrors is that if you had these 2 mirrors pictured and also one that was doing the same thing but in the z direction, it would flip around both the x, y, and z components of whatever hit it. So it makes a retroreflector. No matter what direction something comes in it, it bounces right back out at the opposite of that direction. So if you want to make a shiny highway sign or something on the moon that you can leave there to bounce lasers off of, you can do that. The answer is going to be this way. So 15 degrees below the minus x-axis, or if you just make your angles like this, we need 180 plus 15. So we're at 195 degrees. So same toolkit. Let's just move to a trickier setup. So same ray coming in. Our first mirror just like that. And our second mirror points like this. So coming in like this, what will our final direction be? Go ahead and work through it. This is just geometry. Uh, so our normal vector come out like this. So if we have 15 degrees here, and 45 degrees here, must be 30 degrees here. Therefore, our angle of incidence is 30 degrees. Our angle of reflection is also 30 degrees. And it would continue and eventually hit this mirror if the screen went lower. So I'll just conserve space by bringing it closer. So our new normal vector. How far off are we? So this vector coming in, we've got 15 plus 30 plus 30. It's 75 degrees here. So we've got 75 degrees here. So on its path out, 75 degrees. So it needs to be 75 degrees below the plus x-axis. Or 285 degrees in this wave. Measuring things. Good on flat mirrors.
I think so. Are there going to be problems like this on our weekly problem set?
There's not the one that's due on Monday, but yeah, there's going to be some mirror stuff. Could be something like this. Seems likely. One due on Monday focuses on the wave picture of light. Yeah, next time around, some mirror stuff. So why mirrors give things that don't quite look right? So if you have something and you get a reflection of it from the mirror in a mirror, the handedness of what you see has changed. If you put up your right hand in a mirror, it kind of looks like someone's left hand. So that's because it doesn't preserve left, right. It preserves the dimensions which are not the dimension normal to the mirror. So if you've got your mirror person standing with their beautifully drawn hand up. The mirror image of this is going to be still beautifully drawn. But if we spin it around, or from this person's perspective, it wouldn't be upside down. It's going to not look like a right hand anymore. Right, left isn't preserved, but what is, say, north and south is preserved. What seems like it was on the north side, still on the north side. What was on the south side, still on the south side. What was up, still up. What was down, still down. But east-west becomes flipped. So flipping one of those is going to change the handedness of something. Much easier to look in a mirror and prove that for yourself. So something to think about. For the picture that we had before, if we put a hand in here, and reflected it off of both mirrors, what kind of hand would it look like? It would be back to looking like a right hand. What if we used 3 mirrors? So we have 2 mirrors there, and we also have a mirror below it. So the light can bounce off the top mirror, the right mirror, and then this bottom mirror here. Flipping its X, its Y, and its Z. Uh, yes, left. So you would get a mirror image of the hand. Where it is now bizarrely large, but a left hand. And then we mirror image it again. Where now it has an extra finger, but it's back to being a right hand. Like if you look at this hand I just drew with your head upside down, it's the same kind of hand as the first hand. And then if we flipped it again, there's no way I can make the 3D picture of that happening, but flipping it one more time would flip the handedness again. So it'd be back to being a left hand again. So how you see something in a mirror is just a bunch of applications of angle in, angle out. So if we're looking at a thing, with an eyeball, to look at it in the mirror, we can look at the top, and we can look at the bottom. And it seems like the light doesn't bounce. We often imagine that light travels in straight lines. From the eye, it seems like the light actually came from over here. For both of these reflections, angle of incidence equals angle of reflection. Same angle, same angle. But the part that was higher up, you looked higher to see, so you get an image of it. So for the light to travel the same distance that it did before in the seeming way to get to this image and the way the light actually traveled, the only way for that to work out is for the distance between the mirror and the object, which we can call our object distance, to be the same as our distance between the mirror and the image, which we shall call our image distance. So an image like this is called a virtual image, because it seems like this object is there, even though the light never actually was on this side of the mirror. Everything over here, everything on the right of the mirror could be pitched blackness, no light at all. There are certain kinds of images called real images that the light actually passes through on the way to your eye, but there's not actually light here. So this is a virtual image. Wanna let it get curved? All right. What if we have a spherical mirror? So an important concept for the spherical mirror is the focal length or focal point. So if we have a curve like this, the focal point is where parallel rays will meet. So we got something normal here. And normal there. Parallel rays are going to bounce and meet at this point here, which is our focus or our focal point. So one way of thinking about what this focal point would be is that is going to be our image distance if we had an object which was infinitely or near infinitely far away. Because if you have something which is close, light coming off of it isn't parallel. If you have something which is farther, the light coming off of it still isn't parallel, but those incoming rays are closer to parallel. So if you have something really, 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 really far away, it's like the light coming from it is parallel. So something from very, very far away would focus at the focal point, or parallel lines coming in focus at this focal point. So where would this focal point be? The two black lines that I drew in are both normal to the surface. So if we draw this out bigger, all lines that are normal to its surface meet in the center of the sphere. So if you completed the sphere, all those normal vectors are going to meet in the center. So we can call that point our center of curvature. So doing some geometry on it, and make a bigger picture just to make it more clear. So same idea, but bigger. Big spherical mirror. And if our light rays come in, we have our normal vectors. Meet. And the reflected rays, which are going to meet. So just doing some geometry. This angle needs to be the same as this angle because they're formed on opposite interior angles of a parallel line, which will be the same as this angle because this is theta incident and this is theta reflected. So all three of those angles need to be the same. So if these angles are all small, then the amount of distance the amount of horizontal distance that needs to be covered to get the same vertical distance will not be the same. Because this red ray coming down has a steeper downwards angle than this black ray coming down. So the red ray hits the center line of this mirror closer to the mirror than the black line does. There's not a precise formula for what it'll hit. If things are wide, it's going to vary based on how wide it is. But if we can assume that the angles are pretty small, then we have, it's going to need to travel twice as far to make the same downwards travel if it's traveling at half the angle. So looking at this, is half as steep an angle as this. So in order for it to descend the same distance, it's going to need to travel twice as far. This does not hold for big angles, but it holds pretty well for small angles. And optics is just chock full of assumptions like this, that it works out good enough for small angles, and we just run with that. These triangles. If we've got the same opposite So this angle in radians is about the same as the sine of the angle. It works as a good assumption in radians for small angles. We just call it the small angle approximation. Makes life nice and easy. So if our opposite over hypotenuse is about the angle, it also works that our tangent is about the same. These are not exact truths. They're good approximations. So if we go ahead and make it, if our tangent is twice as big and the opposite side is just as big, that means our adjacent side needs to be half as big. So what that adds up to is the distance to the focus is the radius of curvature divided by 2. And we will be using this even though it's not perfect. So to see the imperfections of this, if you look to bigger and bigger angles, something comes in from way far from that central axis of the mirror. It doesn't quite meet at the same focal point. So the fact that this idea of all of the rays meeting at an exact focal point, if they come in parallel, not quite holding up, is called spherical aberration. If you used a parabola instead of a sphere for your mirror, it actually would work. And if you use a small enough curved surface, so if you just don't let your curve continue past this part here, it holds good enough. But the broader the curve, the more you find that light rays that hit at the edges don't meet at the same spot from light rays that hit near the center. But it works good enough to use. So we've got a focal point where parallel things will meet. Yes, the focal point is the directrix for a parabola. And for most of what we're doing, we're just going to say it's about the same curvature, even though it doesn't quite get it right. So this is a little bit of lie, but we use it anyway. So what if things are not coming in parallel? What if our object is not infinitely far away? So if we've got our focal point and our radius of curvature, and let's just say an object here. So doing some geometry, we can get a pretty good idea of where it's going to make an image, where the light rays that leave this are going to meet up. So if a light ray leaves our object and does come in parallel, parallel rays go through the focus. And the opposite works also. If a light ray goes through the focus, drop a little better. Light ray goes through the focus. I don't know if that was better or not. It's going to leave parallel. So an image is going to form around over here. There is a mathematical equation for where it will form. One over the distance to the object plus one over the distance to the image is equal to 1 over the focus.
What sort of a number are we putting in for the focus? Is that like distance from the center to the focus?
Yes. So all of these things you would measure with units of length. So these are all lengths, so meters. You can work in centimeters or whatnot, but same length unit for all of them. So it's our focal length that's being put in here. So to just show where this comes from, I get my picture back a little better. So if a light ray hits the exact center, well, its normal line is already drawn in. That's just our central axis of the mirror. So then it needs to just make a nice mirror image like that. And if it comes in parallel, it would go through the focus. And if it goes through the focus, it's going to come out parallel. So things should be meeting up around there. So our height has changed. So sometimes you might notice you look at something in a curved mirror or your funhouse mirror, things look bigger or smaller. So the magnification or changed in height is based on the change in distance. Because these angles are the same, the farther that image ends up from the mirror, the more it's grown. So we call that its magnification. Or the ratio of the height of the image over the height of the object. So in this case, we're upside down. So it needs to be minus our distance to the image or our distance to the object. And a second set of triangles can be made. Where instead of looking at hitting the mirror itself, you look at going down to the focus and then going from the focus to the mirror. So this triangle is similar to this triangle. So that means that our object height over our image height we're just keeping the ratio the same, our image height over our object height needs to be equal to this length here divided by that length there. So one of them is the distance to the focus from the object. And the other one is the distance from the focus to the mirror, or just the focal length. So in order to solve for what our image distance needs to be, we have two different things which the image height divided by the object height must be equal to. So setting them equal to each other, pretty cool. So dividing everything, oops. I'm gonna flip these fractions around. And then divide both sides by DO. So the right side is just going to turn into -1 over the image distance. And our other side. Where did I go wrong? I flipped it over. I flipped it over. Sorry. Image that follows. Oh, that's what I did wrong. I'm sorry. I flipped the sides of this fraction. The image side is F, and the object side is DO minus F. So if I flip it over, sorry that I flipped it around the first time. So then dividing every side by the object distance. We get focus -1 over object distance. Equals 1 over the image distance, or there it is. Sorry, I got confuzzled on the intermediate steps. So this lets you just algebraically figure out where an image is going to pop out. There are a few difficulties to using this. One of them is some things can be negative. The focal length can be negative. And you might end up with a negative image distance. So what if instead of having a mirror like this, there are light rays coming in? We had something which is convex. So when the incoming rays hit the convex mirror, so cave bending inwards like a cave does, convex isn't that. They're not going towards a focus. So finding a focal length seems a bit odd because it's not focusing. But it looks like they came from one. It seems like all the light is coming from here. So this just becomes a negative focal length. Or if it's on the other side of the mirror, it just counts as negative. And for our radius of curvature, it's still twice the focal length. But we would just also count that as negative for this setup. So I've a couple practice, one with a concave mirror and one with a convex mirror. So set it up, see if you can go through the numbers. And remember, this is the radius of curvature, not the focal length. So we're going to have our object, our radius of curvature, our focus, and our mirror all evenly spaced. So to follow the equation, 1 over our object distance plus 1 over our image distance equals 1 over our focus. First, we need to know what that focal length is, which I already gave, because our radius of curvature is twice the distance to the focus. equals R/2. Ten centimeters. 1/30 cm plus 1/, our image distance, 1/10 centimeters. So it works out for 15 centimeters. So our image is going to be right there. So to draw what the rays would do, if say something went in parallel, it's going to go through the focus and then there. If something went through the focus, it's going to leave parallel. If something hit the exact center of the mirror, it's all going there. That's what our light rays would be doing to get there. So this image is real. The light rays actually do pass through this point on a way to an eye, which could be farther from the mirror than that. So there's a real image which is formed there. Good on this one? Let's flip that mirror around. Same situation, one little change. So our object. Now our mirror is convex. So our focus and our radius of curvature. So yeah, see if you can get this one. It is negative, but not that far. So it comes in parallel. It's going to bounce away as if it came from the focus. if something goes towards the center, it's just going to mirror reflect. It seemed like it came from over there. So we're actually going to end up on the other side and within the focus. Closer? We have 1 over project distance plus 1 over image distance. It's 1 over our focal distance. So we now have a negative 20 radius of curvature, so a negative 10 centimeter focal length. So subtract 1 over 30 centimeters from each side. And it works out to be negative 7.5 centimeters. So negative just means on the other side. So it works out to be a virtual image that time. The light doesn't actually come from the image. Light never passed by there. It just seemed like it was radiating outwards from that point. So virtual instead of real. Also, it is right side up because our magnification is minus our image distance over our object distance. So our negative image distance is going to cancel out that minus sign and give us something which is right side up. So it doesn't flip over, it shrunk, but right side up, and the light didn't actually come from there. We are going to deal more with mirrors next week. And we're also going to deal with refraction. It's going to be our biggest topic for next week looking forward. So how light bends if it enters something with a different n or index of refraction. So the fact that it travels at different speeds is going to bend it by different amounts. And we're going to look to how that works, how much bend we get. All right. That'll be it for today.
Thank you, Professor.
Thanks, Professor. Have a good holiday.
You too.
So Professor, would like glasses, would those be convex because that way it would be right side up still?
So you can make things like glasses with whatever kind of curvature, but they work on light passing through them instead of reflecting light. So instead of having one surface, they have two to think about, the front and the back. So we will deal with how glasses work next week. We need to get to how light bends when it enters a surface and also how it's going to bend when it exits.
Okay, yeah, because that's more like a lens than a mirror, right?
Yes.
Okay.
Glasses are lenses.
Yeah. Okay.
Pairs of them. Yeah.
Got it. Thank you, Professor.
So
See you
yeah,
next
we'll
week.
do those next week.
Yeah.
Sure.
All right.
Professor,
Yes.